Hello everyone, welcome back to EC Fundamentals 1. This is another example of KVL. Here we're going to learn how to apply KVL in a circuit to find out an unknown voltage drop. Here's a circuit we're going to be dealing with. It includes a 20 volt ideal independent voltage source, and then it includes a bunch of resistors connected the way that you see here. The unknown part that we're trying to find here is this voltage drop Vy, which is shown here as the voltage drop across that resistor R4 with the assumed polarity. Once again, if no one had given you the polarity, you would have to assume one and solve the circuit. Now, at first glance, this circuit is a little bit more complicated than what we have seen here. For example, it includes more components, but perhaps even worse, it actually includes more than one loop. So just by looking at it in the very beginning, you might feel a little bit confused, because if you try to apply KVL, it's not always going to give you an answer. Somebody, for example, might say, what if I apply KVL in this loop right here? Perhaps for many of you, this is the most obvious loop that we can look at. Well, the problem in that case is that the voltage drop across R2 is not known, and the voltage drop across R3 is also not known. And unfortunately, there doesn't seem to be an easy way to find these voltage drops because the current is not known through either of the resistances either. So unfortunately, we really can't find the voltage across R2 or 3 by applying Ohm's law. Even in another way, maybe somebody else could say, all right, well, I do know this 20 volt source, so perhaps I should include this in my loop. But then as I walk around and I come back to my source, I face the same problem. The voltage drop across R1 is not known, again across R3 is not known, so how can I really proceed and find that? So there is another path which obviously is going to give us the right solution, and the right path to follow here, I'm going to use my red color, is to include the 20 volt, is to include the 15 volt, and then come down and include Vy. The reason that I can choose that path is, first of all, KVL applies for any closed path, so I can really choose any path I like. But in this particular path, I only have 3 circuit components, and the voltage drop across 2 of them is actually known. For example, for the voltage drop on the ideal voltage source, I have 20 volts, and across R5, I have 15. So all I have to do is apply KVL in this perhaps not immediately obvious closed path and find the solution. So once again, I'm starting from my lowest left corner, which I just put on the circuit. I'm moving clockwise, exactly as shown by the red line. And then if I see the negative sign first, I put the voltage drop as negative. If I see the positive side first, I put the voltage drop as positive. So here I will have negative 20, which is the voltage drop I see first, plus 15, which is the voltage drop across R5, plus Vy is equal to 0. So indeed, I have just a single unknown, and so Vy here is going to be equal to just 5 volts. So clearly the numerics here are very easy. You don't have to spend too much time as long as you choose the right path. And the big comment I'd like to make here is that even though normally we are kind of focused in seeing the small loops, like this loop right here, or perhaps this bigger loop right here, KVL applies in every closed path, and you should keep in mind, even if the very first path you see is not the most obvious one, you should explore perhaps there is a better path you can apply KVL and get the solution you need in maybe the best possible way. So thank you very much for watching this video. We will see you next time.